Good evening, everybody. Can you all hear? Can you hear? Okay. Right. This is what we will do. Now, your waves practicals generally start from sonometer. From sonometer practical up to non-parallax method, concave lens. We can finish all the practicals and there's no issue. Is it there? We can finish all the practicals. There won't be a particular issue. It's a very simple practical set, but guaranteed you have marks. Guaranteed one structured essay. Guaranteed you have marks. Okay, no? Right. The first practical is the sonometer practical. The first practical. So we'll write and do this. Sonometer practical. In your practical booklet, it's practical number 12. Practical number 12. Right. Have a look. This is practical number 12. Practical number 12. Practical number 12. Right. Finding the frequency of a tuning fork. Finding the frequency of a tuning fork using a sonometer. Finding the frequency of a tuning fork using a sonometer. Can all of you all hear? Is it clear? Can all of you all hear before we start? If I talk from here, can you all hear? Increase the volume. If I talk from here, can you all hear? Is it clear? Clear. Okay. Right. Okay. So finding the frequency of a tuning fork using a sonometer box. Listen very carefully. Now, the sonometer box is a hollow device. The sonometer box is a hollow device. That means inside there is air. Air can pass through, move in, move out. Is it clear? Air can pass in, move in and move out. Here we have connected a string, metallic string, here to a particular bridge. Here to a particular bridge. There to a particular bridge. Okay. Here you have a pulley. Here you have a pulley. And that is connected to a system where you can place weights. System where you can place weights. Okay. System where you can place weights. So listen carefully. What we do is, first of all, before we start the experiment, now what we are doing here is, finding the frequency of a tuning fork using sonometer. So finding the frequency, unknown frequency, okay, unknown frequency. So this is what we are doing. We are going to change the masses here and find the resonance length. And find the resonance length. Okay, change the masses here and find the resonance length. So what we do is, we bring both the bridges close to each other. We bring both the bridges close to each other. And what we do is we place a paper rider in between. We place a paper rider in between. What do you mean by paper rider? Just a piece of paper that is bent. Okay? Just a piece of paper that is bent. So what we do is we put a paper rider there. And these are two wooden bridges. These are two wooden bridges. So you have a wooden bridge. You have a wooden bridge. And a paper rider there. So if I name this, that is a paper rider. That is a paper rider. Right. Have a look. Right. Listen. Now you have the sonometer box, you have the wooden bridges, and you have the paper rider. Before the experiment starts, remember this: there should be some tension in the string. There should be some tension in the string. So what we do is we initially suspend a 0.5 kilogram load. A 0.5 kilogram load. So there is an initial tension acting there. Okay. So there is an initial tension acting there. Right. Now look at this carefully. Look at this carefully. Don't worry about the recording one because it's going on YouTube live. So next you can watch it. There's no problem. Don't concentrate. Don't type and wait. Concentrate. So here you go. Wooden bridges kept very close by, paper rider, and a 0.5 kilogram weight initially to give tension. Okay? Initially to give tension. Right. Now what do you do? Now there's a tuning fork. So all of you all know a small, I'll give a small summary of the tuning fork. So a tuning fork consists of a prong and a stem. So these are prongs. And here you have the stem. Here you have the stem. So what we do here is very simple and very direct. You take the tuning fork and you hit it with a rubber pad. There's a rubber pad connected there. What you do is you hit it with a rubber pad. When you hit it with a rubber pad, don't knock it on the table. Don't do that. The moment you start to knock on the table, you have a problem. Okay? The moment you start to knock on the table, you have a problem. Take the rubber pad and knock it. So it's like a hammer. So you sometimes like a hammer. So you have a rubber pad here. So you have a rubber pad there. You knock on the rubber pad. So when you knock on the rubber pad, this is what you should do. You knock on the rubber pad, and that will cause the tuning fork to vibrate. That will cause the tuning fork to vibrate. So once the tuning fork vibrates, very important, how do you keep the tuning fork on the sonometer box? Fork on the sonometer box. Well, these are you keep the tuning fork on the sonometer box. You place on the sonometer box, I'll draw it separately. One. You place it on the sonometer box such that the stem is touching the box. the stem is touching the box. So when the stem touches the box, the vibration from the prongs will transfer. Okay? The vibration from the prongs will transfer to the box. So here you have vibration. Here you have a vibration. The vibration will transfer to the prong, through the stem to the nail. Okay? Through the stem to the stem. So why rubber band? Next question. If you use a metal on metal now, if you take a tuning fork, it's made of metal. Metal on metal will cause the metal to change shape, or the tuning fork to change shape. When the tuning fork changes shape, what happens? Frequency will change. So we cannot alter the frequency. We must make sure that the frequency is always what? Fixed. So you can't do anything with the tuning fork. So you can't heat it, because the moment you heat it, the length will change, therefore frequency will change. You can't load it, that means you can't apply wax or whatever, frequency will change. So you make sure that the vibrations are what? Done according to the very minimum vibration given. So you use a rubber band. Yeah, you use a rubber band. I'll show you later in videos how this particular thing is done. For now, we'll just go through. So once it vibrates, you place it on the sonometer box such that the vibration transfers to the sonometer box. So vibration transfers to the sonometer box, right? Now look at the word carefully. All of you all know the concept of resonance. What do you mean by the concept of resonance? If the external frequency is equal to the natural frequency of the object, large scale amplitude vibrations take place. When the external frequency is equal to the natural frequency, large scale amplitude vibrations take place. So when large scale amplitude vibrations take place, what happens is resonance will take place. This will start vibrating violently. Okay? This will start vibrating violently. Look at the board. So what we do is, now all of you know the theory. What is your base theory? F is equal to 1 over 2L square root T over simple F. Square root T over simple F. Now, we have one tuning fork. One particular wire. So material say. So we are supposed to change the length with the tension. We are supposed to change the length with the tension. Now, how will you change the tension? The only way you can change the tension is make sure that the tension is changed by the weight here. So when the weight changes, the tension will also what? Change. Okay. Weight changes, tension will also change. Right. Look at the board carefully. Look at the board carefully. So now what? Frequency is here. Fixed. One tuning fork. Set of tuning forks. Next experiment. So one tuning fork. You are trying to change. You are trying to find the tuning fork frequency. One single wire. So material of the wire is same. Linear density is same. One frequency is given. So the only way you can draw a graph is change the length and the tension. How do you change the length and the tension? The only way to change the length and the tension is you change the weight that is put there. Okay? You change the length that is put, weight that is put there. So here we go. So this is what you are doing. F equals 1 over 2L square root T over simple M. F equals 1 over 2L. I'm putting a weight there, load capital Mg, simple M. Square both sides. Square both sides. F squared is equal to 1 over 4L squared. Capital Mg over simple M. Capital Mg over simple M. So what you are going to do here is, what are you doing? You are changing the mass that is hung there. You are changing the mass that is put there. So that means you are changing M. And you are measuring M. Therefore, if you simplify this, L squared is equal to make L squared the subject. 1 over 4 F squared, simple M, and of course G is there, capital M. So what are you changing? You are changing the mass, that is your X. and you are measuring the vibrating length y, and your graph is of the form y is equal to mx. Now I have still not taught you how to find the length. I'm just giving you the connection. F equal 1 over 2L square root T over L. T is the weight tension. Tension capital Mg over simple L. Square both sides. You can't change the frequency because you have one tuning fork. That's not a variable. That's a constant. What are you going to change? You are changing the weight and you are finding what? The vibrating or resonance length. So L square is your dependent variable. Independent variable is the mass you place there. Clear? Right. Now look at this carefully. Look at this carefully. Right. When you have a simple M is the mass per length. Correct. Simple M is the mass per length. So simple M is here. Capital M is there. Okay. Simple M is here. Capital M is here. Right. Now look at this carefully. How do you find the resonant length? How do you find the resonant length? Look at the board. Very, very carefully. I'll show it to you here. So you have the sonometer box. You have the sonometer box. You have the wire. Here you go. We have two bridges connected here. We have two bridges connected here. Bring both the bridges very close to each other. Bring both the bridges very close to each other. And place the paper either there on top. Place the paper either there on top. There. Place the paper either there on top. Here you have sonometer box. We vibrate the tuning fork. We vibrate the tuning fork. Correctly, you place at the center of the sonometer box between the two bridges. Now remember, the sonometer box is not a 2D diagram. Sonometer box is 3D. If I show a mini version of it, it's like this. So you have wire going this way, wire going that way. So it's 3D. There is space here. So you vibrate the tuning fork and you keep it there, exactly there. Preferably, you keep it between the two bridges. Normally, that's what we do. You vibrate the tuning fork, and we place it at the center of the sonometer box between the two bridges. Okay? Center of the sonometer box between the two bridges. And then what we do is, we move the movable bridge. We move the movable bridge. When we move the movable bridge, we slowly start moving. At one instant, frequency of the tuning fork and frequency of vibration of the wire both will be same. Frequency of the tuning fork and frequency of the vibration of the wire both will be same. Then resonance will take place. Why? External force frequency. What is your external force frequency? Tuning fork. Natural frequency of the wire both will be equal. Resonance will take place. When resonance takes place, paper rider will fly. Paper rider will fly. So what we do is, we vibrate the tuning fork, keep it at the center of the sonometer box. We move the movable bridge until the paper rider flies out. Okay? Until the paper rider flies out. These are the gaps in the sonometer box. They are gaps. Just like the hollow part of a guitar. Yeah? Hollow part of a guitar. So you move the movable bridge. You move the movable bridge. You move the movable bridge. At one instant, you move the movable bridge. At one instant, resonance will take place. What do you mean by resonance? This will vibrate at the fundamental mode. This will vibrate at the fundamental mode. Resonance will take place. Paper rider flies off. Paper rider flies off. Paper rider flies off. So once the paper rider flies off, what you do is you measure the length from this center to that center. That is your vibrating length. That is your vibrating length. Okay? Remember, now some people think the wire and the sonometer are connected, the tuning fork and sonometer are connected. No. If I draw it in 3D for all, the wire is here. The tuning fork is kept on the sonometer box. The wire is somewhere here. The wire is somewhere there. The tuning fork and the wire are not touching each other. Okay? The tuning fork and the wire are not touching each other. The vibration energy is transferred to the sonometer box. From the sonometer box, air particles start vibrating. Air particles will start vibrating, will transfer the energy to the wire. The wire will start to vibrate. Okay? The wire will start to vibrate. Then the external force frequency of the tuning fork is equal to the natural frequency of the wire. Is equal to the natural frequency of the wire. Then what happens is resonance will take place. Resonance will take place. So then we measure the length between the two bridges. We measure the length between the two bridges. Clear? So again from the beginning, before you write this. So we have a sonometer box. Quickly answer. Why does the sonometer box have two hollow openings? Because air is free to move. Yeah, air is free to move. We have two bridges, wooden bridges. There's a pulley there, preferably a smooth pulley. If it's not smooth, you put some grease and all, make it a bit smooth. And then you have a weight hanger, and there's a set of weights. You have a set of weights. So initially you put the wire in tension. Initially put a weight of 0.5 kilogram with some tension. Vibrate the tuning fork and place it on the sonometer box. Place it on the sonometer box. So when you place it on the sonometer box, one bridge is fixed. We start moving one of the bridges. This is your fixed bridge. That is your fixed bridge. This is your movable bridge. This is your movable bridge. That's your movable bridge. You move the movable bridge until the paper rider flies off. Until the paper rider flies off. What do you mean by the paper rider flying off? Paper rider flying off means very simple. Very simple. The frequency of the tuning fork is equal to the frequency of the wire. Therefore, resonance has taken place. When resonance takes place, large scale amplitude vibrations take place. Large scale amplitude vibrations take place. When large scale amplitude vibrations take place, this paper rider will fly off. Once this paper rider flies off, you measure the vibrating length. What you should do is, for the same mass, you repeat the experiment at least 3 times. You repeat the experiment at least 3 times. After repeating the experiment at least 3 times, what you do is you measure the length and you get the average length. Understood? Don't take one reading. One reading if you take, it's not good. Okay? Then what you do is, you must make sure that for this one reading, if you take, problem. So without for the one reading, you take continuous reading. 3 readings and then find the average. Okay? 3 readings and then find the average. Three readings, then find the average. How do you plot the graph? How do you plot the graph? Now, somebody is asking, why should we move the bridge? Right? No, good question. Why should we move the bridge? We cannot get resonance. We cannot get resonance unless what? The length is changed. What do you mean by the length is changed? What do you mean by the length is changed? Look at this carefully. We have only one tuning fork. Only one tuning fork. So that is not a variable. That is not a variable. We have only one type of wire. Simple M is the same. One type of wire. Simple M is the same. So the only way you can change is length and weight. The only way you can change is length and weight. That is why mass is your independent variable, length is your dependent variable. You keep one fixed and you are moving the other. That's because you are trying to change the length. If you start moving both, then doing the practical with the tuning fork, you are keeping the tuning fork, trying to move it, all of that together you can't do. That is why we keep one fixed and we are moving the other. So it's easy to take the measurement. Understood? Why does resonance occur? Simple answer. Frequency of the wire will change its length. All of you know. F is inversely proportional length. This particular tuning fork, there is a particular frequency which is connected to a length. Yeah, which is connected to a length. That is why you must change the length. Now here you are changing the weight. When you are changing the weight, the vibrating length will change. When you change the tension in the wire, the vibrating frequency will change. When the vibrating frequency changes, the length will also what? Change. Very simple. So what you do there is, for 0.5 kg mass, you find the vibrating length. Once you find the vibrating length for 0.5 kg mass, then what you do is, you start changing. You increase the load by 0.5 kilogram intervals. You are increasing the load by 0.5 kilogram intervals. That means initial 0.5 kilogram, find the vibrating length. I add another 0.5 kilogram, then this is 1 kilogram, find the vibrating length. Like that, I keep adding 0.5 kilograms. I start finding the vibrating length. I start finding the vibrating length. Like this, if you can take about 7 to 8 values, more than enough. Okay? 7 to 8 values, more than enough. So what we do is, for different masses, best is, remember, for one weight, you repeat the experiment minimum 3 times. One weight, repeat the experiment minimum 3 times, find the average. And you mark the average here. Once you mark the average, here it's going to be L squared. You can find L squared as well. Now you can plot the graph. If you plot the graph, M is going to be in kilogram. L squared, let's say meter squared. Graph is of the form y is equal to mx. Y is equal to mx. You can find the gradient of the graph. Gradient of the graph. What will the gradient of the graph give you? Gradient of the graph is G for x squared M. G divided by 4x squared. Now, how do you find the mass per length? Don't forget, huh? Mass per length is what? Area into density. Area means you must find the diameter of the wire. Pi d squared over 4 into density. So there is one more additional measurement that you should take. What is the additional measurement that you should take? You should take the diameter of the wire. Diameter of sonometer wire. Tell me, what is the most suitable instrument to take the diameter? The most suitable instrument you have to take is micrometer screw gauge. Use the micrometer screw gauge to find the diameter. Once you find the diameter using micrometer screw gauge, look at the board now. Very simple. You know the gradient. Gradient means you take a point here, x1, y1. You take a point there, cutting the graph, x2, y2. Gradient is equal to y2 minus y1 divided by x2 minus x1. y2 minus y1 divided by x2 minus x1. So I put here for the gradient y2 minus y1 divided by x2 minus x1. G divided by 4 pi 4 square f square is equal to g over 4m gradient. I won't put the whole thing. 4m gradient. F is equal to square root g divided by 4m gradient. Remember, gradient find separately, mass per length find it separate, and then do the substitution. Okay. Density of the wire from a lab manual you must find. Okay. Density of a wire from a lab manual you must find. Using from a lab manual, substitute there. Let's say copper. Copper density is freely available. You need to measure. From that you can find what? Frequency. Okay. From that you can find the frequency. Okay, no? Right. Shall we write this? Don't touch it. Then the vibration is distorted. Somebody is asking, why shouldn't the vibrating tuning fork? Why shouldn't the vibrating tuning fork touch the sonometer wire? When the thing is vibrating, if it touches the wire, what happens? The vibration is stopped. It should never touch. You allow the natural vibration to take place. The vibration should be transferred to the box through the stem. Okay, no? There. Somebody is asking, why area is pi d squared over 4? You should know this by now. Huh? It's okay. Pi r squared. Radius is diameter divided by 2 square. You get pi d squared over. Okay, no? Let's write. Let's write this. Apparatus needed. So, theory students, take this as a note. Huh? Apparatus needed. Let's write. A sonometer. A sonometer. A tuning fork of unknown frequency. A tuning fork of unknown frequency. A tuning fork of unknown frequency. A set of weights 0.5 kilogram mass. A set of weights 0.5 kilogram mass. A set of weights 0.5 kilogram mass. A paper rider. A paper rider. A paper rider. A meter ruler. Rishma is asking, can't we find the mass per unit length by measuring the mass and length of the wire? Can. That's another method. We can take a piece of the wire, measure the mass, measure the length, and then divide. Mass per length is simple. Okay? These are common methods that they ask. That was I'll give as additional point. Okay. Right. You can write that. Triple beam balance. Piece of the sonometer wire. Triple beam balance. Piece of the sonometer wire. Okay. That's right. Procedure. As shown in the figure below, we fix the wire to pass over a pulley. We fix the wire to pass over a pulley such that the wire is in tension. 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 We bring both the bridges close to each other. We bring both the bridges close to each other. We bring both the bridges close to each other. And we place a paper rider in between. And we place a paper rider in between. And we place a paper rider in between. As shown in figure 1. As shown in figure 1. As shown in figure 1. Second point. We vibrate the tuning fork. We vibrate the tuning fork. And place it at the center of the sonometer box. And place it at the center of the sonometer box. Place it at the center of the sonometer box. Between the two bridges. Between the two bridges. Between the two bridges. And move the movable bridge. And move the movable bridge. And move the movable bridge. Until the paper rider flies off. Until the paper rider flies off. As shown in figure 2 and figure 3. 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 And we measure the vibrating length. And we measure the vibrating length. And we measure the vibrating length. By measuring the distance between the two bridges. By measuring the distance between the two bridges. By measuring the distance between the two bridges. Okay. By measuring the distance between two bridges. Put a small note and write. Put a small note and write. for a particular mass, for a particular mass, we at least repeat this experiment for a particular mass. We at least repeat this experiment 3 times. For a particular mass, we at least repeat this experiment 3 times. And we find the average vibrating length. And we find the average vibrating length. And we find the average vibrating length. Okay. Right. Next point. Next point. We increase the weights in 0.5 kilogram intervals. We increase the weights in 0.5 kilogram intervals. We increase the weights in 0.5 kilogram intervals. And we plot a table. And we plot a table. And we plot a table between M and L. Between M and L. We plot a table between M and L. We plot a table between M and L. And we sketch a graph. And we sketch a graph between M and L square. And we sketch a graph between M and L square. We sketch a graph between M and L square. Using the gradient of the graph. Using the gradient of the graph. Using the gradient of the graph. We can find the unknown frequency. 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 Put a small note. Put a small note. Note. To find the unknown frequency, we should know the mass per length. 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 We can find the mass per length using the following 2 methods. We can find the mass per length using the following 2 methods. We can find the mass per length using the following 2 methods. Roman number 1. First method, Roman number 1. Easy one, huh? Take a piece of the sonometer wire. Take a piece of the sonometer wire. Take a piece of the sonometer wire. Measure its mass and length. Measure its mass and length. Measure its mass and length. Take a piece of the sonometer wire, measure its mass and length. From this, we can find the mass per length. From this, we can find the mass per length. Right? Second method. Second method. First, write this in mass per length is area into density. Right? Mass per length is area and density. Area is pi d squared over 4 times density. Right? Write this part. Mass is area into density. Area is pi d squared over 4. Somebody has forgotten. That's how you get pi d squared over 4 into density. Okay. Now next time, using a micrometer screw gauge, we find the average diameter of the wire. We find the average diameter of the wire. We find the average diameter of the wire. And using a lab manual, we can find the density. And using a lab manual, we can find the density. Using a lab manual, we can find the density. Using a lab manual, we can find the density. From this, we can find the mass per length. From this, we can find the mass per length. Okay. From this, we can find the mass per length. From this, we can find the mass per length. Okay. Right. Few of them have asked, do we need to stand? Niduli, I think, has asked, do we need to stand it on the sonometer box? Yes, you must place the stem. The stem should touch the sonometer box. Here, stem is touching the sonometer box. You can't just hold near. You can't hold near. Why? From the stem to the box will vibrate the air particles. Air particles will in return vibrate what? The box through the string. The box vibrating, only the sound comes, resonant sound comes. So prong vibration goes to the box. Box vibration will go through the string, and the string will vibrate. Okay, now? Right. We don't know, using the gradient of the graph, we can find. You hold with your hand. You can, with your hand, you can hold it. Right. Okay. Quickly draw this down. Quickly draw it. Don't waste time. Quickly draw. Figure number 1. These are the vibrations are transferred. Quickly draw. Okay, finished. Yes. Method one is acceptable. Find the mass, divide by the length. That's why they give a triple beam balance. Finished. Okay. Figure number 2. Figure number 3. Draw. Paper idea is a small piece of paper here like this. Small piece of paper. Like a V shape. To keep on the wire. Okay. I'll show the video, the practical video. First you'll write and finish it. Otherwise, this and the video you can't watch together. No? Okay. Quickly draw. Finished. Finished. Still drawing. Quickly draw. Code is clear, no? Right? Okay. Okay now? Once you're writing slowly, take a photo and then maybe complete it. Right. Next time, right? Put the table. Now put the table. Mass, length, L square. Put mass, length L square. Mass, length and L square. Quickly. Mass, length and L square. The reason why we keep the tuning fork on the sonometer box between the bridges, so the energy is transferred more efficiently. Give us, no, I'll send them again. Right, once you finish the table, now write the equation. Write the equation. F equal 1 over 2L square root T over L. This is the weight that you are hung. Simplify it. Bring the relationship y equal mx form. Bring the relationship y equal mx form. Write the equation. Finish. Finish. Last line. Draw this, then write the equation. No sentences, just write the equation. Finish. Anybody miss the note? Later you can ask in the group. Somebody will put the final note. Okay. Right? Right. Now plot the graph and how to find the frequency. Plot the graph and how to find the frequency. Plot the graph and how to find the frequency. You can write that. Finish. Okay, now. Okay, done. Right. Practical number 30. Practical number 13 is verification of the relationship between frequency and length. Actually, these are all standard relationships. I don't know why we have to verify this in A-levels, but they have given it now. They have asked verify Charles law, verify pressure law. I don't know why we have to verify, because they are anyway laws, but they have given it as a practical. So we have to do. Same method, but now you have a addition. You have a set of tuning forms, not one tuning form. Now you have a set of tuning forms. So what I do is these basic things you all know. I'll erase. Right. What we do now is we don't change the mass. Now we are verifying a relationship between length and frequency. We are verifying a relationship between length and frequency. Practical number 30. Verifying relationship between frequency and length. This is what we do. We connect a 2 kg weight here. Fixed, no change. We connect a 2 kg weight, and now we have a set of tuning forks. What do you mean by set of tuning forks? Prong lengths are different. Prong lengths are different. If I take F1, F2, F3, F4, F5, you all tell me which tuning fork has the highest frequency? First tuning fork or the last tuning fork? First tuning fork or the last tuning fork? First tuning fork. Shorter the prong length. Remember, the stem lengths are equal. We look at the prong lengths. Shorter the prong length, greater the frequency. Right. Shorter the prong length, greater the frequency. Right. Now what do you do? Now what do you do? Remember, we must start from a very small vibrating length and then increase. All of you all know the theory. Frequency is inversely proportional length. So higher the frequency, smaller the vibrating length. So what we do is we start the experiment with the tuning fork having the highest frequency. We start the experiment with the tuning fork having the highest frequency. So we take tuning fork F1, we hit it on the rubber pad, place it at the center of the sonometer box, move the movable bridge until the paper either flies off. That means no need to draw this again. Same procedure. Yeah, same procedure. Move the movable bridge until the paper either flies off, and we measure the vibrating length. Then what we do is we take the next tuning fork. Next tuning fork is F2. When the frequency reduces, the vibrating length will increase. So if I take the next tuning fork, frequency is lesser, vibrating length is more than what we measure. So from there we can continue. No need to come again for the beginning. From here we went gradually, paper either flew off. Once we take the next tuning fork, the vibrating length is more than this. So no need to start again from the beginning. From here, place a paper either, vibrate, move, again paper either goes. Again measure the length. Then we take the next tuning fork. Repeat the procedure. Like that, we repeat the procedure for each tuning fork and we find the vibrating length. My advice to you, as usual, for every tuning fork, repeat this experiment 3 times. Find the average vibrating length. Why? Sometimes the paper either might fall early. Sometimes the paper either might fall late. Sometimes something might happen, it might get stuck to something and then therefore it won't fall. Later it will fall. Therefore, at least take the reading 3 times and find the average. Earlier, one person was asking this. I think I have answered your question. That is why we find the average vibrating length. Okay, that is why we find the average vibrating length. So we start with the tuning fork having the highest frequency, measure the vibrating length. Then we move in order of the frequency reduced, or the frequency is reducing this. Frequency will reduce that. And we measure the vibrating length. And we measure the vibrating length. Right. Now what's going to happen? Look at it. All of you know the equation. F equal 1 over 2L square root T over simple L. Tension we don't change. 2 kg, no change. Mass of the wire we won't change. So F is equal to 1 over 2 square root T over simple L into 1 over L. But what is our independent variable? What are we changing? We are changing the frequency. So independent variable frequency, dependent variable length. So you cross multiply L 1 over 2 square root T over M 1 over L. Plot a table. For a particular frequency, find the vibrating length. Find the vibrating length. Find 1 over L. For a particular frequency, let's say I'll name this in. For F1, find the vibrating length. For F2, find the vibrating length. F3, find. F4, find. F5, find. And then you find 1 over F. Plot the graph between 1 over F per second or per hertz and vibrating length in meters. It is a graph going through the origin. L proportional to 1 over F, therefore F proportional to 1 over F. If by any chance, or guaranteed you will get this, length 1 over F graph is y equal mx form, we say frequency is directly proportional to 1 over F. That is the relationship. Clear? That's right. That's right. Practical 30. Verifying the relationship between frequency and vibrating length. Verifying the relationship between frequency and vibrating length. Okay. That's right. Apparatus needed. Apparatus needed. This is your practical garment booklet. Sonometer box. Sonometer box. Set of weights. Set of weights. Light paper rider. Light paper rider. Okay. That's right. Procedure. We fix the apparatus as shown in figure 1. We fix the apparatus as shown in figure 1. We fix the apparatus as shown in figure 1. And we place a 2 kilogram weight. And we place a 2 kilogram weight. Now in the set of weights only 2 kg is there. That's why they are given set of weights. And we place the 2 kg weight, 2 kilogram weight. Such that the tension will exist in the wire. Such that the tension will exist in the wire. Bring both the bridges. Next point. Remember, experiment means you must draw a graph. You can't write equations and get. So that's why this practical. We bring the both bridges close to each other. We bring the both bridges close to each other. We bring both bridges close to each other. And we place a paper rider in between. And we place a paper rider in between. And we place a paper rider in between. Paper rider in between. Next point. We take the tuning fork with the highest frequency. We take the tuning fork with the highest frequency. We take the tuning fork with the highest frequency. We vibrate it and place it on the sonometer box. We vibrate it and place it on the sonometer box. We vibrate it and we place it on the sonometer box. Between the two bridges. Between the two bridges. Between the two bridges. And we move the movable bridge. And we move the movable bridge until the paper rider flies off. And we move the movable bridge until the paper rider flies off. And we measure the length between the two bridges. And we measure the length between the two bridges. And we measure the length between the two bridges. And we measure the length between the two bridges. Next point. We then take the next tuning fork. We then take the next tuning fork, it's a better set 2. We vibrate it, place it on the sonometer box and repeat the experiment. We vibrate it, place it on the sonometer box and we repeat the experiment. And we repeat the experiment. Until the paper rider flies off and we measure the vibrating length. Until the paper rider flies off and we measure the vibrating length. Until the paper rider flies off and we measure the vibrating length. Next one. We repeat the above procedure in descending order of the frequency. We repeat the above procedure in the descending order of the frequency. In the descending order of the frequency. In the descending order of the frequency. And we measure their respective average vibrating lengths. And we measure their respective average vibrating lengths. Measure their respective average vibrating lengths. Average vibrating lengths. We table the values. We table the values we table the values. And we plot a graph between L and 1 over F. We table the values and we plot the graph between L and 1 over F. L and 1 over F. If it is a linear graph, we can write the relationship as shown below. We can write the relationship as shown below. We can write the relationship as shown below. Okay. Find the equation. L proportional to 1 over F, therefore F proportional to 1 over F. L proportional to 1 over F, therefore F proportional to 1 over F. Okay. Right. Quickly draw this. And then the next page. So practical 12, practical 13 done. Next we have resonance tube practicals. Practical 14, practical 15. Quickly write down. Okay, next one. Finish. Finish drawing. Have you all finished drawing? Okay. Right now. Equation, table, graph. Okay, finished. Done. Okay. Right. Next is practical number 40. Practical number 40. Practical number 14. Right. Finding the velocity of sound in air. Finding the velocity of sound in air. Finding the velocity of sound in air. And the end correction using a resonance tube. And the end correction using a resonance tube. Using a resonance tube. So there are two practicals in this. Practical 13 is using a single tuning fork. Practical 14 is using a set of tuning forks. Okay. So practical 14 is using a single tuning fork. Practical 15 is using a set of tuning forks. Both methods are very simple. Same method. So what do you need? First one, using a tuning fork. So using one tuning fork. The heading is finding the velocity of sound in air. Finding the velocity of sound in air. And the end correction using resonance tube. Okay, right. So what do we need? we need a tall water vessel. Tall water vessel. We need a resonance tube about 2.5 centimeter diameter and 50 centimeter length. 50 centimeter length. So you have water field here. You have water field there. You have water field there. And people don't talk about this. Yeah, people don't talk about this. But generally we fill the bottom with sand, or if it's possible, we put cotton. Sand or cotton. I'll tell you the reason why. Sand or cotton at the bottom. There's a reason I tell you. Then we connect a linear scale here. We connect a linear scale here. We connect a linear scale. And then of course there is a stand connected. There you go. Right. This is what we do. We always start with a very small vibrating net. We are using a single tuning fork. We vibrate the tuning fork and place it on top of the resonance tube such that it is symmetrical. Place the prongs on top of the resonance tube such that it is symmetrical. And then what we do is we pull the resonance tube out. We pull the resonance tube out. When we pull the resonance tube out, two things can occur. The first loud sound is heard. The first loud sound is heard. Quickly stop. First loud sound is heard. Now the loud sound will be like this. Now these are a perfect example for resonance. Can you hear? But here the resonance is in a different way. The wire is vibrating here. That's vibrating the air inside. Can you see? That's vibrating the air inside. And you hear a loud noise. So it won't be loud like this, but this is a resonance noise that is heard. Is it clear? It's a resonance noise that is heard. Something similar. Okay? Something similar. So what happens is, you pull the resonance tube out until the first loud sound is heard. So when the first loud sound is heard, we quickly go and measure the vibrating length. Now this was like the earlier one. For the same tuning fork, you repeat it at least 3 times and get the average. Why? We might hear it late. We might hear it early. Those kind of things are there. Depends on our hearing or and our judgment. So you repeat at least 3 times, find the average. This will give you first or fundamental mode of resonance. In correction. So we can easily write this lambda divided by 4 L1 plus n correction, equation 1. Then what we do? We vibrate the tuning fork, keep it over the resonance tube, pull it further. From here, pull it further. When you pull it further, the second loud noise is heard. Second loud noise is heard. When the second loud noise is heard, means that's your next harmony, third harmony, first overtone vibration. First overtone vibration. There you go. Next vibration. Now we can say here, quarter and half, 3/4, 3 lambda divided by 4, L2 plus N correction equation. Now what we are going to do is, now this tuning fork frequency we know, frequency of tuning fork is N. Now we have to calculate. How are you going to calculate? First of all, let's find the velocity with subtract. 2 minus 1. 3/4 minus quarter lambda divided by 2. Subtract L2 minus L1. From here, lambda 2 times L2 minus L1. From here, lambda 2 times L2 minus L1. So 2 times L2 minus L1. From this, we can say B is equal to F lambda. Frequency of the tuning fork we know. Lambda is 2 times L2 minus L1. 2 times L2 minus L1 velocity. B equals 2F L2 minus L1. There you go, velocity. 2 times L2 minus L1. There you go, the velocity. Okay, no? So here you go, velocity of sound. How do you find the N correction? How do you find the N correction? Substitute 1 to 2. All of you know 3 lambda over 4 L2 plus E. What is lambda over 4? L1 plus N correction. L2 plus N correction. 3L1 plus 3E. L2 plus N correction. Simplify. 3L2 minus simplify. 2E equals L2 minus 3L1. N correction is L2 minus 3L1 divided by 2. There you go, N correction form. So how are we doing this experiment? We are doing this experiment using a single tuning fork. Single tuning fork. We find the first mode or first harmonic. Remember, the first harmonic is also fundamental mode. Fundamental mode. We find the vibrating well. Then we find the third harmonic. Third harmonic. Third harmonic is also known as first overtone. First overtone. Right, there you go. So I did tell you all, why are we using sand or a piece of sponge here? Why? Remember, when you vibrate the air column here, there will be a water wave travel. This water wave will go hit the bottom and reflect. This water wave will go hit the bottom and reflect. I'll show it here. Separately, I will show it because I think you should know. These are things that are there, so you should know. Here you go. Bottom sponge. So when you vibrate the tuning fork, here a small water wave vibration occurs, hits the bottom. If you have a sponge or sand, reflection is stopped. If you don't have sponge or sand, reflection will occur and this surface will never be stable. It won't be at rest. It will always be what, shivering or unstable because the water waves are reflecting and coming back. Understood? Is it clear? Is it clear? If the wave vibration occurs, this wave vibration will travel, hit the bottom and reflect without this sponge or sand. Once it reflects here, whatever interference will take place. And this surface will never be stable. So to keep this stable, we can put sponge or sand at the bottom. Okay? Sponge or sand at the bottom. Okay. Right. So that's the experiment. That's the experiment. That's right. Apparatus needed. Apparatus needed. Resonance tube of diameter 2.5 centimeter. Resonance tube of diameter 2.5 centimeter. Resonance tube of diameter 2.5 centimeter and length 50 centimeter. And length 50 centimeter. And length 50 centimeter. Okay. Next one, comma, a tuning fork of known frequency. A tuning fork of known frequency. Meter ruler. Meter ruler. Stand. Stand. Tall water vessel. Tall water vessel. Tall water vessel. Okay. Right. Let's write procedure. First one. We set the apparatus up as shown in the figure. We set the apparatus up as shown in the figure. We vibrate the tuning fork. We vibrate the tuning fork and place it just over the mouth of the resonance tube. And place it just over the mouth of the resonance tube. And place it just over the mouth of the resonance tube. Place it just over the mouth of the resonance tube. And we vibrate the air column inside. And we vibrate the air column inside. We vibrate the air column inside. We vibrate the air column inside. We then gradually pull the resonance tube out. We then gradually pull the resonance tube out. We then gradually pull the resonance tube out. Until the first loud sound is heard. 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 This is the fundamental mode of vibration. This is at the fundamental mode of vibration. This is at the fundamental mode of vibration. And we measure the vibrating length L1. And we measure the vibrating length L1. And we measure the vibrating length L1. We measure the vibrating length L1. Next one. Next one. We vibrate the same tuning fork. We vibrate the same tuning fork. We vibrate the same tuning fork. Place it over the resonance tube. Place it over the resonance tube. Place it over the resonance tube. and further pull the resonance tube out. And further pull the resonance tube out. And further pull the resonance tube out. Until the second loud sound is heard. Until the second loud sound is heard. Until the second loud sound is heard. This is at the third harmonic. This is at the third harmonic. This is at the third harmonic. And we measure the vibrating length L2. And we measure the vibrating length L2. And measure the vibrating length L2. Right. Right, precautions. Right, precautions. To get more accurate values for the vibrating length. To get more accurate values for the vibrating length. To get more accurate values for the vibrating length. For the same resonance state, we repeat the experiment at least 3 times. For the same resonance state, we repeat the experiment at least 3 times. We repeat the experiment at least 3 times. We repeat the experiment at least 3 times. And we find the average vibrating length. 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 Next precaution. To avoid reflection of the water wave from the bottom. To avoid reflection of the water wave from the bottom. We can use sand or a sponge or sand or cotton. So that's sponge cotton. We can use sand or cotton placed at the bottom to avoid reflection of water wave from the bottom. We place sand or cotton at the bottom. We place sand or cotton at the bottom, so that reflection does not take place. 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 Okay. Right. Draw these two, write it, then calculate. First one is a calculation method. Second one is set of tuning forms. Quickly work. Quickly write down. Okay. Quickly write down. Quickly write down. I'll give you 1 point. Why are we keeping exactly at the center? So we are keeping exactly at the center such that what? The energy of vibration is transferred symmetrically or uniformly throughout the whole column. Finished. Finished. Let's write. Let's write. We must place the tuning fork symmetrically over the resonance tube. We must place the tuning fork symmetrically over the resonance tube. We must place the tuning fork symmetrically over the resonance tube. Such that the vibration energy is uniformly transferred. Such that the vibration energy is uniformly transferred throughout the trapped column of air. Throughout the trapped column of air. Throughout the trapped column of air. We place the resonance tube symmetric. We place the tuning fork symmetrically over the resonance tube. We place the tuning fork symmetrically over the resonance tube. Such that the vibrational energy is uniformly transferred throughout the trapped air column. Throughout the trapped air column. Throughout the trapped air column. Okay. Right. Practical number 50. Practical number 50. Using a set of tuning forks. You're right. Using a set of tuning forks. Finding the velocity of sound in air. Finding the velocity of sound in air. Finding the velocity of sound in air. And the end correction. Finding the velocity of sound in air and the end correction. Finding the velocity of sound in air and the end correction. Okay. How are we going to do this? Just like the earlier practical. How are we doing the earlier practical? Now we have a set of tuning forks. We have a set of tuning forks from highest frequency to lowest frequency. So here you have F1, F2, F3, F4, F5, F6, so on. So we start with a small vibrating length. Tell me, if you are starting with a small vibrating length, you'll use the highest frequency or the lowest frequency. All of you all know what highest frequency, that's the rule. If I use the highest frequency tuning fork, vibrating length is going to be very, very small. So I start with the tuning fork F1. And remember, we always concentrate only on the fundamental mode of vibration. There's a reason for that. If you take the intensity of sound, because we are listening to resonant sound, since you are listening to resonant sound, look at this carefully. Intensity of sound. Intensity of sound. And here you have overtone number or harmonic number of vibration. Harmonic number. You can take first harmonic, second is not there, third harmonic, fourth is not there, fifth harmonic, sixth is not there, seventh harmonic. To take it here, at the first harmonic only you have the highest intensity. There's an increased highest intensity in the first harmonic. Third harmonic, the intensity is lower. Fifth harmonic even lower. Seventh harmonic even lower. So when the intensity is low, it's difficult to identify. Therefore, the easiest method to identify is always using what? The first harmonic. So we do the experiment always for the fundamental mode of vibration. Okay. We do the experiment always for the fundamental mode of vibration. We'll go. So if I write the equation lambda divided by 4, L plus n correction. Lambda is 4 times L plus n correction. B is equal to F lambda 4 times L plus n correction. Now, what is your independent variable? Frequency, right? You have a set of tuning forks. Simplify this. Independent variable is set of tuning forks. Dependent variable is length. L plus E is B over 4 times 1 over F. L is equal to B over 4, 1 over F minus E. If you simplify this, L is equal to B over 4, 1 over F minus E. Graph is of the form y is equal to mx minus c. Mx minus c. So what do? We first use the tuning fork. Having the highest frequency. Highest frequency vibrate on top, pull the resonance tube out, first loud noise is heard. Measure the vibrating length. Then take the next tuning fork. We are doing this in decreasing order of the frequency. When the frequency reduces, vibrating length will increase. Do it. Pull the resonance tube out. First loud sound is heard. We repeat this for all the tuning forks. We repeat this for all the tuning forks. And we also measure 1 over F. Now what? Plot the graph between 1 over F and L. L sometimes in centimeters, this is in per hertz. You will get a graph like this. If you extend the graph, y-intercept is there. Y-intercept is there. From the gradient of the graph, we can find the velocity of sound in air. 4 times gradient. Y-intercept in connection. Finished. That's the experiment. So what do we do? Fix the apparatus as shown in the figure. Use the tuning fork with the highest frequency first. Start with a very small vibrating length, pull the resonance tube out until the first loud sound is heard. Measure the vibrating length. Now remember, like I said earlier, for every tuning fork, repeat the experiment at least 3 times and then find the average. Okay. Then take the next tuning fork, vibrate over the resonance tube where you stop. Where you stopped here, from there start. Pull the resonance tube out until the loud sound is heard. When the loud sound is heard, what happens? Measure the vibrating length. Okay. Measure the vibrating length. Repeat the procedure until all the resonance tubes are found. Until all the frequency tuning forks are found. Plot the graph. Using the gradient, you can find the velocity of sound in air. Using the y-intercept, you can find the end direction. Okay, now let's write it and then we'll have a small break. Okay, let's write. Apparatus needed. Apparatus needed. Tall water vessel. Tall water vessel. Resonance tube. Tall water vessel. Resonance tube. Meter ruler. Meter ruler. Meter ruler. Stand. Set of tuning forks. Set of tuning forks. Set of tuning forks. Let's write procedure. Let's write procedure. We fix the apparatus as shown in the figure. We fix the apparatus as shown in the figure. We fix the apparatus as shown in the figure. And we start with a very small vibrating length of air. And we start with a very small vibrating length of air. And we start with a very small vibrating length of air. We start with a very small vibrating length of air. Next point. Next point. We use the tuning fork with the highest frequency. We use the tuning fork with the highest frequency. We use the tuning fork with the highest frequency. Place it over the resonance tube. Place it over the resonance tube. Place it over the resonance tube. And gradually pull the resonance tube out. And gradually pull the resonance tube out. And gradually pull the resonance tube out until a loud sound is heard. Until a loud sound is heard. Until a loud sound is heard. And we measure the vibrating length of air. And we measure the vibrating length of air. We measure the vibrating length of air. Next point. We repeat the above procedure. We repeat the above procedure in the descending order of all the frequency of the in all the frequencies of the tuning fork. In the descending order. In the descending order of all the frequencies of the tuning fork. Of all the frequencies of the tuning fork. And we measure the vibrating length of air. And we measure the vibrating length of air. And we measure the vibrating length of air. We measure the vibrating length of air. We then plot a graph. We then plot a graph between L and 1 over F. Between L and 1 over F. Between L and 1 over F. Using the gradient and the y-intercept. Using the gradient and the y-intercept. We can find the velocity of sound in air. We find the velocity of sound in air and the y-intercept and the eddy correction. Sorry. Using the gradient and the y-intercept, we find the velocity of sound in air and the eddy correction. We find the velocity of sound in air and the eddy correction. We find the velocity of sound in air and the eddy correction. Right precautions. Right precautions. Precautions. That's right. For every tuning fork, we repeat the experiment at least 3 times. We repeat the experiment at least 3 times. We repeat the experiment at least 3 times. And we find the average. And we find the average. We repeat the experiment at least 3 times and we find the average. Next one. We always consider the first harmonic for the practical. We always consider the first harmonic for the practical. We always consider the first harmonic for the practical. This is because it has the greatest sound intensity. It has the greatest sound intensity. It has the greatest sound intensity. Okay. It has the greatest sound intensity. Right now. This part is same as the earlier one. Quickly draw it back. Set of tuning forks, table, and then the graphs. 50 draw. Today my plan is to finish up to practical number 18. Practical number 18. And then we'll have another session like that. So we can do the spectrometer practical and the convex lens practicals. So practical 18 up to critical angle method, today we will cover. Right. Okay. Have you finished writing? Okay. Right. Next one, draw this. Intensity of sound. Okay. Draw. If you write this out. If you write this one, I'll do that. Okay. It is here on the board. Okay. Okay. Right. How about a 20-minute break and come? Then we have practical number 16, 17, 18. 16, finding the refractive index of glass using real depth, apparent depth. 17, finding the deviation of light using a prism. 18, finding the prism angle using critical angle method. Finding the prism angle using critical angle method. Right? So have a small break and come. After the break, we'll continue. Okay. Right. Okay. Next one. Practical number 16. Practical number 16. Practical number 16. Finding the refractive index of glass. Finding the refractive index of glass using a traveling microscope. Using a traveling microscope and a block of glass. Using a traveling microscope and a block of glass. Right. So it's a very simple practical actually. This is what we do. On a white sheet of paper, we make a mark. On a white sheet of paper, we make a mark. And using the traveling microscope, we focus on this mark. So using the traveling microscope, we focus on this mark. Okay. And we get the reading. Then what we do, on top of this mark, we place a glass block. On top of this mark, we place a glass block. All of you all know by now, glass block means if I'm looking from top, this is the actual depth. That is the actual depth. We will see the image at a much more shorter depth, somewhere here. That's where the image is. And now we focus this image using the traveling microscope. We focus this image using the traveling microscope. We focus this image using the traveling microscope. So here we say reading is X. Let's say here the reading is Y. Now on top of this, we place the glass block and we place a small lycopodium layer. What layer? Lycopodium layer. Lycopodium layer is like a powder now. Sometimes we can't find lycopodium in your school lab. They use baby powder. Baby powder is used. A small thin layer is placed. Now why are we placing a small thin layer? So that we can't see the bottom. We can't see this cross. Okay. We can't see this cross. So lycopodium powder. Lycopodium powder. And what we do is, using the traveling microscope, we focus on the top surface and we get the reading. We focus on the top surface and we get the reading. Reading is Z. Reading is Z. Right. Now what is your theory? Refractive index equal real depth divided by apparent depth. Now it's a good chance for you to remind all work. Refractive index equals real depth divided by apparent depth. What is your real depth? If you look at this, real depth is the actual depth here. That is reading Z minus reading X. Here bottom, here slightly gone on top, so Z is bigger. Then you have apparent depth. What is apparent depth? Apparent depth is the difference between these two. Z minus y. Z minus y. Top surface and then where the image is. Difference between these two is the apparent depth. So now you know the equation. Now you know the equation. What is the equation? Refractive index of glass equals real depth divided by apparent depth. Real depth divided by apparent depth. Do the substitution. Refractive index of glass with respect to air. Real depth is Z minus X. Apparent depth is Z minus Y. There you go. Real depth over apparent depth will give you the refractive index. Will give you the required refractive index. Right. Okay, no? Let's side. Let's side. Apparatus needed. Apparatus needed. Traveling microscope. Traveling microscope. Traveling microscope. Rectangular glass block. Rectangular glass block. White sheet of paper. White sheet of paper. Some lycopodium powder or suitable powder. 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 Let's write. Procedure. Procedure. Make a mark on a white sheet of paper. Make a mark on a white sheet of paper. Make a mark on a white sheet of paper. And using a traveling microscope, focus on that mark. And using the traveling microscope, focus on that mark. Using the traveling microscope, focus on that mark. And obtain the reading X. And obtain the reading X. Focus on that mark and obtain the reading X. Obtain the reading X. Right. Second point. Place a glass block. Place a glass block on top of that mark. Place a glass block on top of that mark and observe from near normal incidence. And observe from near normal incidence. And focus on the image of the mark. And focus on the image of the mark. Focus on the image of the mark. And obtain reading Y. And obtain reading Y. And obtain reading Y. Obtain reading Y. Next point. Place a very thin layer of lycopodium powder. 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 So that we cannot see the cross mark through the glass. So that we cannot see the cross mark through the glass. So that we cannot see the cross mark through the glass. So that we cannot see the cross mark through the glass. And focus on the top surface of the glass mark. And focus on the top surface of the glass mark. Focus on the top surface of the glass mark. Focus on the top surface of the glass mark. And obtain reading Z. And obtain reading Z. Next point. Using readings X, Y, Z. Using readings X, Y, Z. Using readings X, Y, Z. We can find the refractive index of glass with respect to air. We can find the refractive index of glass with respect to air. We can find the refractive index of glass with respect to air. We can find the refractive index of glass with respect to air. Okay. Right. Put a precaution. Precaution. Make sure that the lycopodium layer is very thin. Make sure that the lycopodium layer is very thin. Make sure that the lycopodium layer is very thin. Otherwise, we will get a false reading for Z. Otherwise, we will get a false reading for Z. Otherwise, we'll get a false reading for Z, which should be the top surface of the glass layer. Which should be the top surface of the glass layer. Which should be the top surface of the glass layer. Okay. Draw. Write down. Finish it. Finish writing. Have you finished writing? So the microscope is moved. You can move the microscope vertically. Quickly, quickly. Two more practicals, practical 17, practical 18. Spectrometer practical, convex lens practical. I will let you all know. If I can, I'll do it tomorrow evening. We'll see. Okay, done, finished. Right. Practical number 17. Practical number 17. Right. Finding the angle of minimum deviation. Finding the angle of minimum deviation. Finding the angle of minimum deviation by a prism. Finding the angle of minimum deviation of a prism. Sorry, of a prism. By observing the variation of the deviation of the ray through the prism. Of the deviation of the ray through the prism. Of the deviation of the ray through the prism. Okay, right. So these are harder practical. I don't know how many people have done this in school. It's a very hard, it takes a lot of time, and you must take a lot of readings. Okay, the readings that are given in your booklet actually are not sufficient. Fluids. You must take a huge amount of readings so that you can actually draw a good graph. Because the graph is a curve that you will get. Okay. So this is what you do. This is what you do. Take a sheet of paper, draw a line like this. Take a sheet of paper, draw a line like this. Once you draw a line, we draw normals like this. We draw normals like this. We draw normals like this. I'll draw a view. Draw a view. And then what we do is, using a compass or whatever, we draw rays. Let's say this angle is 20 degrees. Then we draw a ray here. This is 30, 40, 45, 50. Like this we draw. We draw many. So we take a sheet of paper, draw normals, and for each normal we measure angle and we draw lines at different angles, 20 degree, 30 degree, 40 degree, 45, like that. 5 by 5 degrees you can go. Generally, the recommended is 10, 5 by 5 degrees also perfect. You can do 5 degree, 5 degree, 5 degree increase also great. Okay. Then what you do? I'll take one and show. Okay. I'll take one and show. Now we have the surface. You have the normal. You have the normal. And you have this angle that you have measured. What you do is you keep two pins. You keep two pins, P1 and P2, around 1 to 2 centimeters away. 1 to 2 centimeters away. The gap should be there. Nice gap should be there. Okay. A nice gap should be there between these two values. Okay. Then what you do is you take the prism. I'll draw in a different color. You take the prism. Exactly keep the prism like this. Exactly keep the prism like this. So that this line is on the midpoint of this section. I'll name the prism ABC. I'll name the prism ABC prism. Look at this carefully. Right? We name the prism ABC. Now what we do is from this side we look. From this side we look the images of these two pins so that the images are exactly in line. They should be along a straight line. You can't see as two images. You must see it as a single image. Huh? You must see it as a single image. Once you see it as a single image, from this side, what we do is we mark two other pins. We mark two other pins in line with that image. We mark two other pins in line with that image. So the images are, if I draw it very carefully, images are exactly in line. Now I'm looking here, I'm not seeing this. I'm looking from here, I can see the image of these. How are those images formed? Images are formed due to partial reflection. So light rays will reflect here, light rays will reflect somewhere there. Here you can see the image of P1. Light rays will reflect here, somewhere else it will reflect. That's the image of P2. So what I do is, from here I can see the images of P1 and P2 in line. I place two other pins, P3 and P4, in line with those images. Then what I do is, I draw the outline of the prism. I draw the outline of the prism and I mark these 2 points carefully. And I mark these 2 points carefully. And I mark these 2 points carefully like this. Now I remove the prism out. When I remove the prism out, what do you all have? This is what you have. Once I remove the prism, this is what you have. The outline of the prism is there. The outline of the prism is there. Outline of the prism is there. I'll name this ABC. These two pins are there, P1, P2. Look carefully. These two pins are there, P1, P2. These two pins are there, P1, P2. And these two pins are here, P3, P4. These two pins are here, P3, P4. Now this line of course is already drawn and finished. We have already marked the normal also. This is your angle of incidence I1. What do I do is I join these two lines with the points in the straight line and I draw a normal there. I then join these two with a straight line. Join these two with a straight line. I must find the angle of deviation. This is your incident. This is your refracted or emergent ray. Angle between them is angle of deviation. Angle between them is angle of deviation. So let's say this example is for 20 degrees. Let's say this example is for 20 degrees. So for 20 degrees, we have found the angle of deviation. Like this, we repeat the experiment for all the angles here. And then what we do is, we plot a graph. Or first, before that, we plot a table. Different angles of incidence, different deviation. Plot a table. Let's say 20 degrees, 30 degrees, 35 degrees, 40 degrees, 45 degrees, like that. And you find the deviations as well. Keep going. Up to about 90 degrees, you can not 90, 85 degrees or 80 degrees work. Plot the graph between angle of incidence and angle of deviation. You will get a graph like this. Different points, you will get a graph like that. From here, you can find the minimum deviation. From here, you can find the minimum deviation. Okay, no? From here, you can find the minimum deviation. Okay. So what's the process again? Take a white sheet of paper. Draw normals at equal distances. Measure angle with the vertical, different angles in 5 degrees Celsius or 5 degree intervals. 5 degree intervals. Then what you do is, on one of the lines drawn, place two pins P1, P2 and the prism. Look from the opposite side AC such that the images of P1 and P2 are in line. Images of P1 and P2 means they occur due to partial reflection. They are in line. Mark it using two other ways. Remove the prism. Join P3, P4 to AC. Draw normal. Join the line here between X and Y. Join the line between X and Y. Extend the incident ray, extend the emergent ray. Find the angle in between. Angle in between is angle of deviation. So for 20 degrees now we know the angle of deviation. Like that. For all the angles we repeat this. Plot the graph. From the graph we can find the minimum deviation. Okay. That's right. Procedure. Apparatus needed. Equilateral glass prism. Equilateral glass prism. Equilateral glass prism. Drawing board, drawing board, drawing pins, drawing pins, white sheet of paper, white sheet of paper, white sheet of paper, 4 optical pins, 4 optical pins, a ruler and a protractor. 4 optical pins, a ruler and a protractor. 4 optical pins, a ruler and a protractor. Right. Let's write procedure. As shown in figure 1, as shown in figure 1, draw a horizontal line on a white sheet of paper. Draw a horizontal line on a white sheet of paper. Draw a horizontal line on a white sheet of paper. And draw normals at equally spaced distances. And draw normals at equally spaced distances. Draw normals at equally spaced distances. Draw normals at equally spaced distances. Using the compass and the protractor, or using the protractor, measure angles in equal, measure angles in 5-degree intervals. Measure angles in 5-degree intervals. Measure angles up in 5-degree intervals. Up to about 80 degrees. 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 Next point. Next point. We then take the prism ABC. We then take the prism ABC and place it such that point X is on the midpoint of AB. Point X is on the midpoint of AB. Point X is on the midpoint of AB. And we place 2 pins P1 and P2. And we place 2 pins P1 and P2 appreciable distance away, and place 2 pins P1, P2 appreciable distance away along the line drawn. Along the line drawn. Along the line drawn. Along the line drawn. Right? Next point. We move the eye along the side AC. We move the line, we move the eye along the side AC. We move the eye along the side AC until the images of P1 and P2 are seen in line. Until the images of P1 and P2 are seen in line. Until the images of P1 and P2 are seen in line. Until the images of P1 and P2 are seen in line. And we then place two other pins, P3 and P4. And we then place two other pins, P3 and P4. And we then place two pins, P3 and P4, in line with the images of P1 and P2. In line with the images of P1 and P2. In line with the images of P1 and P2. In line with the images of P1 and P2. Keep writing. We draw the outline. We draw the outline. We draw the outline of the prism. We draw the outline of the prism. We draw the outline of the prism. And we remove the prism. We draw the outline of the prism and we remove the prism. We draw the outline of the prism and we remove the prism. Full stop. Next point. We join P3 and P4 with a straight line. We join P3 and P4 with a straight line. We join P3 and P4 with a straight line. Until it meets AC at Y. 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 Next point. We join XY with a straight line. 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 Next point. We extend the incident ray. We extend the incident ray. And we extend the emergent ray. We extend the incident ray and we extend the emergent ray. And find the angle in between. And find the angle in between. And find the angle in between. This will give us the angle of deviation. 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 We repeat the above procedure. Next point. We repeat the above procedure for all the angles. We repeat the above procedure for all the angles. And we draw the graph between angle of deviation. And we draw the graph between angle of deviation and angle of incidence. And angle of incidence. Angle of deviation, angle of incidence. And we find the angle of minimum deviation. 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 Okay, no? Okay. Put a small sign, right? Images of P1 and P2 are formed. Images of P1 and P2 are formed due to partial reflection. Due to partial reflection. Due to partial reflection. Okay. Due to partial reflection. Right. Draw. Quickly draw. After this, one more practical. Quickly draw. Okay. Next one. Carefully draw. Okay. Okay. Right. Final practical of the day. Practical number 80. Practical number 80. Right. Finding the refractive index of a prism material. Finding the refractive index of a prism material using critical angle method. Using critical angle method. Using critical angle method. Quickly. Okay. Okay. Done. Right. Critical angle method, very famous when they ask questions. Okay. Very famous. Huh? Right. So these what they do. Take a white sheet of paper. Very simple practical also. Take a white sheet of paper, keep a prism. Take a white sheet of paper, keep a prism. Draw it like this. Right. All of your knowledge practicality. Take a white sheet of paper, keep a prism. And draw the outline. Prism is ABC. Prism is ABC. Prism is ABC. And draw the outline. Then what you do is, you place an optical pin touching or very close to the surface of AB. We place an optical pin very close to the surface of AB. What's the reason? We want light rays to directly go inside the prism. We don't want refraction to take place. We don't want refraction to take place from AB. We want light rays directly to go inside. Okay? Directly to go inside. Then what we do is, we move the eye from C to B. We move the eye from C to B until the image of P1 is just about to disappear, on the verge of disappearing. That means the moment I move my eye slightly away, it will disappear. So move the eye from C to B until the image of P1 is just about to disappear. And then what we do is, we place two other pins. We place two other pins in line with that image. We place two other pins in line with that image. That is all there in the practical. The rest is construction. You have to construct it. You have to construct this. Look at this carefully. Yeah? So we keep a prism ABC on a white sheet of paper and we draw an outline. Place a pin P1 touching the surface AB. Just touching the surface AB. Just touching the surface AB. Move the eye from C to B. move the eye from C to B until the image of P1 is just about to disappear. Until the image of P1 is what? Just about to disappear. So you place two pins P2, P3 in line with the image of P1. In line with the image of P1. Right. Practical done. Now comes a very important part, the construction. The construction. So this is the construction that we're going to do. Construction number one. Construction number one. Look at this carefully. We'll use black line. First one, outline all drawn. P1, P2, P3 also marked. So you mark the points. P1 also marked. Right. This is what you do. First things first. From P1, draw a normal to AC. From P1, draw a normal to AC and extend it such that P1E equals EF. This distance and that distance both are same. So for P1, draw a perpendicular to AC. Extend it such that P1E equals EF. So I'm extending this line such that this is normal perpendicular. We extend it such that P1E equals EF. Right. That's your first geometrical construction. Then what do you do? Join P3, P2 with a straight line. Join P3, P2 with a straight line until it meets point D on BC. Point D on BC and draw a normal. Point D on BC, draw a normal. Point D on BC, join P2, P3, draw normal at D. Draw normal at D. Then what do we do? Join FD with a straight line. Keep a ruler and draw. My one is not straight. You can see it's not straight. Join DF with a straight line. You all keep a ruler and nicely draw. Join DF with a straight line. It will meet here at G, no? Draw a normal at G. Normal at G. Normal at G. Then what? Join P1G. Join P1G. Join P1G. Join P1G. Once you join P1G, then what do? You measure this complete angle. Now, some of you all might be wondering, why is this about on the verge of disappearing? Why, if I move my eye somewhere here, it's going to disappear? Look at this carefully. If I move my eye somewhere here, the line of vision is somewhere there. The angle made there is going to be smaller. Light rays will refract out. Light rays will refract out. Now at this moment, actually what's happening is light rays are undergoing critical reflection. That's why we call it critical angle method. I'll show it in a live file. Not on this diagram, separate diagram I'll show. I'll show it here. What's happening is, now when I look from here, this is only P2, P3. Yeah? P2, P3. Line of vision is there. This is G. This is P1G. The moment I move the eye somewhere here, my line of vision is somewhere there. When I join this angle is smaller than that angle. Understood? I think I'll draw this separately on a new page and show you. Here you go. Huh? Here you go. I'll go ahead on top. Like this. So if I keep my eye here, P2, P3 is there. Line of vision is here, G. Here P1 is there. Critical angle, critical reflection. Light ray is going this way and reflection as well. The moment I move my eye here, line of vision is somewhere there. Now if I draw the normal here and join this, is this angle less than the critical angle or more than the critical angle? Tell me. Is it less than the critical angle or more than the critical angle? Less or more? Less. Less means light rays will go out. That is why we see it as disappearing. We say image disappear. That's because light rays are not turning, they will go out, refract out. So when we are watching just about to disappear, on the verge of disappearing means it's reflecting at critical reflection. It's reflecting at critical reflection. Somewhere here, total internal loss occurs. If you keep your eye somewhere here. That's why we are moving it this way until critical reflection occurs. Is it clear? Understood? Is it clear? Now, why are we moving it from one side to other side when it's just about to disappear? Just about to disappear means critical angle. Just this side means angle made with the normal is less than critical angle. Angle made with the normal less than critical angle means light rays go out, reflect out. So these are the reasons. Now what we do is final one, 6 point number 6. Point number 6 is we measure this angle completely. Actually, this is critical, this is critical. You measure the full angle. Find P1GD. P1GD. That is equal to 2 times critical angle. Critical angle is P1GD divided by what? P1GD divided by 2. P1GD divided by 2. So how can you find the refractive index? Very simple. NG sin C, NA sin 90. That's the rule. So what is refractive index of glass? 1 over sin C. What is 1 over sin C? Sin. From here we can say refractive index of glass 1 over sin C, 1 over sin P1 GD divided by 2. Right. Done. P1 GD divided by 2. I'll separately edit. Write it somewhere here, different place. NG sin C, NA sin 90. NG is equal to 1 over sin C. 1 over sin C is P1 GD divided by 2. There you go. Refractive index of the prism material found. Refractive index of the prism material found. Okay, right. We can also find the critical angle between glass and water. Same method. We can find the critical angle between glass and water. How is that? What we do is same method. Take the prism ABC. Take a glass slide. Take a glass slide. Touch it on water and fix it on the side of AB. Touch it on water and fix it on the side AB. Touch it on water and fix it on the side AB. So here you have water. Here you have water. Water. Now what? Now same method. I want to ask you a question. Critical angle glass air around 42. Critical angle glass water how much? Critical angle glass water around what? 60 odd. Glass air 49 odd, 48 odd. Glass water 60 odd, 62, 63, something like that. Now I take you back to tell me. When I look from here, I get for glass. This is 42. If I look from somewhere here, this angle becomes smaller. So if critical angle is going to be more than 42, more than glass, where should I place my I and C? Which moment will the image disappear? Will it image when my eye is on the right hand side, closer to this edge, or will it disappear towards the left hand side edge? Right hand side edge or left hand side edge? Very good, very good. Right hand side edge. Now you can see the connection. The moment you keep your eye here, line of vision is somewhere here, this angle is going to what? Increase. Understood? Clear, no? So I think now you have a better understanding of this. How do you find this? But why does it disappear? It disappears because of a line of vision. Line of vision is there. If it makes a critical angle, I can see the image. If I move my eye, I can't see it. Why? The angle made is less than critical, light rays will go out. If I move my eye somewhere here, my line of vision is this point. If I join P1 here, this angle is large. So total internal reflection can take place. So in this case, glass water means critical angle is large. No? So guaranteed glass water, I will be seeing it from this side. Guaranteed glass water, I will be seeing it from this side. Look very carefully. I move the eye. First I keep same, no change. Pin P1 touching the surface AB. Why? We want light rays to directly come. Move the eye from C to B until the image is just about to disappear. Now your eye will be somewhere very close here. Then you do the same geometrical construction. Image is just about to disappear. Place two pins P2 and P3 in line. P2 and P3 in line. Appreciable distance away. Now comes the geometric construction. Now comes the geometric construction. From P1, draw a normal to AD or AE. Extend P1E until P1E equals EF. Until P1E equals EF. Until P1E equals EF. Next one. Join P2, P3 with a straight line until it meets BC at D. Until it meets BC at D. Draw a normal. Draw a normal. Join FD with a straight line. Use a ruler. Join FD with a straight line. This point is point G. Join P1G with a straight line. Draw a normal. After that, draw a normal. Or draw a normal, then join P1G. Then what do you do? Now critical angle here is C1, C1. Measure the G dash. P1 G dash F. That is 2C1. Same method. Pin is kept at the same place. But where we see where critical reflection occurs is going to be different depending on the critical angle. Okay, no? So here water, here glass slide. We can find the critical angle there. C1 is equal to P1 G dash F divided by 2. Okay, no? So the major questions they'll ask you, where is the image of P1? Image of P1 is at F. Can you see why we draw this? Because this surface will act like a mirror. Object distance equals image distance. So image of P1 is at F. We move the eye from B to C until the image of P1 is just about to disappear. And we mark 2 points P2 and P3. And we mark 2 points P2 and P3. Draw perpendicular from P1 to AC. Extend P1E equals here. Join P2, P3, meet at D. Draw normal. Join FD. Point G dash. Draw normal. Join P1 G dash. Measure P1 G dash D. Half of that angle is the critical angle. Glass, water interface. Okay. Is it clear? Is it clear? Right, let's write. Let's write. Apparatus needed. Equilateral prism. Equilateral prism. Drawing board. Drawing board. Drawing board. Drawing pins. Drawing pins. White sheet of paper. White sheet of paper. White sheet of paper. Few optical pins. Few optical pins. A ruler and a protractor. 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 That's right. Procedure. Procedure. Place the prism on a white sheet of paper. Place the prism on a white sheet of paper. Place the prism on a white sheet of paper and sketch the outline. And sketch the outline. And sketch the outline. And sketch the outline. Next point. Next point. Place a pin P1. Place a pin P1. Place a pin P1 touching the surface AB. Place a pin P1 touching the surface AB. Place a pin P1 touching the surface AB. And move the eye from C to B. And move the eye from C to B. And move the eye from C to B. Until the image of P1 is just about to disappear. Until the image of P1 is just about to disappear. Until the image of P1 is just about to disappear. Until the image of P1 is just about to disappear. And we place two pins P2 and P3. And we place two pins P2 and P3 in line with the image of F. 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 Sorry, in line with the image of P1. Sorry. In line with the image of P1. It's formulated image of P1. Right. Keep writing. We now draw the outline of the prism ABC. We now draw the outline of the prism ABC. We now draw the outline of the prism ABC. And we mark the positions of the pins and remove the pins. And we mark the position of the pins and remove the pins. And we mark the position of the pins and remove the pins. Right. Okay. Next slide, subtopic geometric construction. Geometric construction. Geometric construction. Keep writing. We draw a perpendicular from P1 to AC. We draw a perpendicular from P1 to AC. We draw a perpendicular from P1 to AC. And extend it. And extend it. Such that P1E equals EC. Such that P1E equals EC. Such that P1E equals EC. Second point. Join P2 P3. Join P2 P3. Join P2 P3 until it meets BC and D. 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 Next point. Draw a normal at D. 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 Join DF with a straight line. 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 Next point. Draw a normal at G. 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 Next one. Join P1G with a straight line. 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 Next point. Measure the angle P1GD. Measure the angle P1GD. Measure the angle P1GD. Measure the angle P1GD. Next you can write P1GD equals to C equals P1GD over 2. Right? P1GD equals to C is P1GD divided by 2. C is P1GD divided by 2. C is P1GD divided by 2. This is how you are moving the eye. Yeah? Next time, right? You can write this equation. Ng sin C equals Na sin 90. Critical reflection. Ng sin C equal Na sin 90. Ng is 1 over sin C. Sin C is P1GD over 2. Right. Sin C is P1GD over 2. Ng is 1 over sin C. C is P1GD divided by 2. P1GD divided by 2. Okay. Ng sin C, Na sin 90. Sin 90 is 1. Ng is 1 over sin C. C is P1GD divided by 2. Okay. Finish writing. Right. Keep about half a page to draw this. Next time, right? Next time, right? Keep half a page to draw this. Next time, right? Find the critical angle between glass and water interface. Finding the critical angle between glass water interface. Finding the critical angle between glass water interface. Finding the critical angle between glass water interface. That's right. Procedure. Point form right quickly. We place prism ABC on the white sheet of paper. We place prism ABC on the white sheet of paper. We place prism ABC on the white sheet of paper. And pin P1 is touching the surface AB. And pin P1 is touching the surface AB. Pin P1 is touching the surface AB. Next point. Dip the glass slide in water. Dip the glass slide in water. Dip the glass slide in water. And place it on surface AC. And place it on surface AC. And place it on surface AC. Place it on surface AC. Move the eye from C to B. Move the eye from C to B. Move the eye from C to B. Until the image of P1 is just about to disappear. Until the image of P1 is just about to disappear. Until the image of P1 is just about to disappear. Until the image of P1 is just about to disappear. And we mark two pins, P2, P3. And we place two pins, P2, P3, sorry. And we place two pins, P2, P3 in line with the image of P1. 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 Next point. We now do all the geometric constructions as earlier. We now do the same geometric constructions as earlier. We now do the same geometric constructions as earlier. And we measure angle P1 G dash D. And we measure angle P1 G dash D. P1 G dash D. Next time, right? P1 G dash D equals to C1. C1 is P1 G dash D divided by 2. P1 G dash D equal to C1. Critical angle glass water interface. P1 G dash D to C1, C is P1 G dash D over. Okay. Okay, now. Right, quickly draw. First, go to the earlier diagram. Earlier we kept half page. Draw this. Or best you start. Start from this. Then you finish with that one. Go earlier. This critical angle for glass. Critical angle. Glass air interface. Glass air interface. Draw. Done, na? Practical 18 done. Draw it down. Finished. Done. Finished. Okay. Next picture. Final one. So you can see actually it takes a long time because you talk and then write the note and everything. So practical 13, 14, 15, 16, sorry, practical 12, 13, 14, 15, 16, 17, 18. 6 practicals done today. Huh? Sorry, 7 practicals. What we have next is spectrometer practical 19 and 20. Then practical 21 is finding the focal length using non-parallax method. Okay. That also will finish off during the week. We'll see tomorrow how I am. If I'm able to stand up and do, I'll do it tomorrow in the evening. I'll let you all know. Now the eye is much more closer to C. Huh? Finished? Drawn and finished? Okay. Right then. Good night. We'll have another session like this. We'll finish off the rest as well. So we just have them discuss, because these waves have a huge section in terms of practicals. So it's good when we have a time like this, we can finish, we can use the class time much more efficiently. Okay, no? Okay then. Take care. Good night. Your liver cleansing time has already passed. Better go and sleep quickly. Take care. Bye. Okay. Good night. Good night. God bless. Now go and directly sleep. Huh? Okay then. I'm waiting till all of you all go. So some of you all must have fallen asleep on the table itself, I think. Okay, okay. Good night. You want me to leave first? I think Kavishal is also putting her eyes up. Okay then. Good night all. Take care. Bye bye. May the force be with you too as well.